Okay, I promised to explain a little bit why the fundamental theorem of calculus works. There's a few things that go into this, and the first is I want to remind you about a theorem we saw before called the mean value theorem. That says if f is continuous on the closed interval ab and differentiable, on the open interval a comma b, then there is a point c in the interval ab where f prime of c is equal to f of b minus f of a over b minus a. So if you recall, if you have a function continuous from a to b, then if you draw the line connecting a f of a and b f of b, then there is a point c, there's got to be at least one point c where the tangent at c has the same slope as the line connecting f of a with f of b. So these two lines are parallel. There's got to be some number c in between a and b where you have the slope being the same as this line here, which is some kind called the secant line, connecting the points a f of a with b f of b. Okay, so perhaps you recall seeing something like that. We used the mean value theorem to argue about whether you could get a speeding ticket without having your speed ever being taken, right? We talked about that. And let's rewrite this in a slightly different way. We have f prime of c times b minus a equaling f of b minus f of a. Okay, so that's the mean value theorem. And there's one more claim I want to make that is going to go into when I try to explain the proof of the fundamental theorem of calculus. This is the following claim. If f is continuous on an interval ab, it does not matter which point in each rectangle you choose to calculate a Riemann sum as the number of rectangles goes to infinity, it wouldn't matter. So this is saying it doesn't matter whether we were doing a left-hand rule, a right-hand rule, a max, min, just some random point chosen to figure the height of each rectangle in a Riemann sum. This is somewhat plausible. Let's draw a picture why, right? If I have tons and tons of little rectangles that I'm trying to figure out, right? Each rectangle, right, this width of this rectangle here, you can see there's not much difference on any of the points that I would choose for the height of the rectangle. It's not going to make a big difference in the area of that rectangle, whether I choose the point I just chose or a point slightly to the left or the right of it. It's not going to matter when there's so many rectangles, right? The more and more rectangles we have, the less and less it seems to matter what value of the function that we pick. So, as long as you're willing to buy the mean value theorem in this claim, I think you can understand a little bit about where the fundamental theorem comes from. So let's write the fundamental theorem again. And this is going to be a brief version of it. The integral from a to b of f prime of x dx is equal to f of b minus f of a. This is a slightly different form here. I'm just assuming we have f prime, right? That's the function we're integrating. We're integrating a function derivative, a function that we know we're integrating the derivative. So that's a statement of the fundamental theorem. How is it the case that this works like this? Okay, well, here's what I'm going to argue. All right. Let's draw our f prime, and let's have a be here and b be here, and let's just divide this into 1, 2, 3, 4 rectangles. So let's call a, we're going to call this x0. This point is going to be x1. This point is going to be x2. This point is going to be x3. And the last one is going to be x4. Okay, so there's going to be some value. We're going to calculate a Riemann sum right here. And right, we want some number in between. We want some number in between x0 and x1, a number in between x1 and x2, a number in between x2 and x3, a number in between x3 and x4 to choose so that we can pick the height of the rectangle. Right? We want to pick some number. Here's what I'm going to argue. In the interval x0 to x1, choose c so that f prime of c times x1 minus x0 is equal to f of x1 minus f of x0. We'll call this C1. How do I know that I can do that? This is the mean value theorem, right? This is the mean value theorem on f, not f prime. We're using the mean value theorem on f. The mean value theorem on f means that some point c in between x0 and x1 exists so that equality is true. I don't know where the C1 is. It doesn't really matter, but let's say it's here. Okay. Now, we're going to take in the interval x1, x2, we're going to choose C2 so that f prime of C2 times x2 minus x1 is equal to f of x2 minus f of x1. So I choose the point for the interval x1, x2 related to the mean value theorem for f. I'm not drawing f. F is just simply kind of imaginary in some sense here, but I know that it's got a derivative, so that means it's continuous and has a derivative, and so I can use the mean value theorem on f. We're using the mean value theorem on the function f to choose the point C2. And then in the interval x2 to x3, I choose C3 so that f prime of C3 times x3 minus x2 is f of x3 minus f of x2. I'm using the mean value theorem again and again and again. And then finally, in the interval x3 to x4, I'm going to choose C4 so that f prime of C4 times x4 minus x3 is equal to f of x4 minus f of x3. Now let's go back and pay attention to our Riemann sum, right? Our Riemann sum says I'm going to add up these rectangles. I've chosen my point to sample the function in the rectangle, or to find the height of the rectangle, right? Each interval I have a point which I'm using to determine the height of my rectangle. And I chose the specific points C1, C2, C3, and C4, which I know exist by the mean value theorem, right? These exist because of the mean value theorem. Now, if I were to try to add up to get the Riemann sum, now this is only 4 rectangles, right? But the Riemann sum would be, let's see, how would I figure out to write this area of all 4 rectangles together? The first rectangle is f prime of C1 times the base, x1 minus x0. The second rectangle's height is f prime of C2, and the width is x2 minus x1. The third rectangle is f prime of C3, is the height, x3 minus x2 is the width, and the fourth rectangle is f prime of C4, and the width is x4 minus x3. All right. That would be the Riemann sum for these 4 rectangles. But now, using this fact, using all of these 4 equalities right here, I can rewrite this Riemann sum. This is f of x1 minus f of x0 plus f of x2 minus f of x1 plus f of x3 minus f of x2 plus f of x4 minus f of x3. Well, look, I've got a lot of cancellation. F of x1 cancels, f of x2 cancels, f of x3 cancels. What's left? F of x4 minus f of x0. x4 is b, x0 is a. So I get f of b minus f of a. So what have I shown? What have I shown so far? I've shown that even with 4 rectangles, if I use the mean value theorem to pick the points that I use to determine the heights of the rectangles, even with just 4 rectangles, if I choose those points exactly right, I get the Riemann sum to be exactly f of b minus f of a. Now I could do that no matter how many rectangles I have. I could keep choosing these points that satisfy the mean value theorem. And so that means that the limit of this process has no choice but to be f of b minus f of a. So indeed, the integral, the definite integral from a to b of f prime dx is f of b minus f of a. Because we've agreed that it doesn't matter which point we choose to determine the height of rectangles as long as the number of rectangles goes to infinity. So if this limit does exist, it has to be f of b minus f of a. All right. That's all I'm going to say about the proof of the proof of the fundamental theorem of calculus. If you were able to follow this, I hope that it has enriched you. If you're not able to follow it, this is not something I'm going to expect you to know or recall. But when I saw this theorem for the first time, I was very amazed. It seemed pretty amazing that it was true. And so since there is a way to explain it to you guys in about 15 minutes why it might be true, I wanted to go through that. Okay, good luck on the web work. I'll see you in a few days.